Welcome to a new video in block 1 of our video series on how to formulate systems biology models into digital twins and combine them with AI. It's part of the course TBMT 42 block 1, and you have more material over here if you want. So in this particular video and in this particular block, we're looking at formulations of different types of model formalisms. And this particular video focuses on reaction-based models. So reaction-based models can typically be summarized into an interaction graph. So an interaction graph is a way to visually represent all of the reactions at the same time. So here we have A forming B in reaction 1, A forming C in reaction 2, and C disappearing into nothing in the elimination reaction 3. And the question that we'll pose here is how to go from this type of interaction graph to a state space form. So an ordinary differential equation, the xdt or x dot, equals some kind of equation here, or some kind of expression. And it's this expression that we'll learn how to write up. And apart from this, there will be an initial condition and a measurement equation that we'll mention shortly, but that we'll talk more about in other videos. So in this video, we will try to find an intuitive reasoning for a general recipe for combining reaction rates, how quickly a reaction goes, into the full ordinary differential equations, the ODEs. And then we will also look at some common alternatives for creating the actual reaction rates. And that will basically end up in an example where we also will deal with inputs and outputs, and show a little bit how this can actually be done in practice, so to say. And first, I want to, before we start, and also at the very end, I will give a disclaimer and a reminder that there are some assumptions behind these formulations here. So, for instance, that the volumes are the same everywhere, and that both the volumes, the temperatures, the pH, and similar sort of complicating factors are constant and not an issue. Okay, so let's start with the intuitive reasoning. So we have a reaction here, 2A plus B becomes 3C. And the reaction rate is here given by V. And let's just start by taking the most simple example possible, where the number of reactions is constant, and it's 25 reactions per second. That's what happens. So V is simply given by 25, and the unit is reactions, which is unitless, so it's just reactions per second, so it's just second to the power of -1. Okay, so that means that each second there will be 2 times 25 A molecules that disappear. And there will be 25 B molecules and 3 times 25 C molecules that appears. So A and B disappears and C appears. So this is basically what we put into the differential equation. How quickly things change. So the differential equation describes the derivative. So what is the rate of change per time of here A? And now it's not A as a sort of chemical name, but it's somehow a quantified value of A. So it can be either the amount or the concentration. And here, since we have reactions given in number of reactions, it's the easiest is to just consider or to count A also in number of A molecules. So that's simply given by -2 times V, so -50, In the same way, B is minus 25 or minus V, and C is given by 3 times V, so 75. So this is the derivative, and the derivative doesn't change because the reaction rate is constant. So it's of course a simplification, but in this particular model, that's simply what we have. And as you notice here, these numbers that stand in front of the reaction names in the reaction, they are important, and they are called stoichiometric coefficients. So we have 2, 1, and 3. And it's also important to note that the 2 and the 1 here, they appear with a minus sign, and the 3 appears with a plus sign when we form the differential equations. And if you have more reactions that also contain A, for instance, then there will be more terms that are of exactly the same nature that just are added onto the differential equation. So the total rate of change of the number of A molecules will be given by this way of adding the information from each individual reaction. So that's basically the whole idea. So it's a quite easy, intuitive understanding of how this works. So let's write it up a little bit more formally. So we have a reaction J, which has some product that has a stoichiometric coefficient Nij for the product Si. And again, it's a product, so here it should be positive, and otherwise it's negative. And if we have this, the stoichiometric coefficient, then we simply sum up that for all of the reactions. Plus sign if it's a product, otherwise it's a minus sign, and the stoichiometric coefficient appears because every time the reaction flows, it's the Nij number that is produced or consumed. Okay, easy peasy. That was sort of what we do once we have the V's, but we need to have some expression for them as well, because they are typically not constant. They typically depend on something, and they typically depend on how many you have of the substrates and possibly also inputs. And here, let's just consider the substrates of a particular reaction here. And the first and simplest, apart from the constant reaction rate, is the mass action kinetics. And this is given by the product. This sign means the product. Before we saw the sum, this is the product. So the multiplication of the concentration or amount, depending on what you choose, of all of the substrates. And here, these stoichiometric coefficients also appear, and here they appear as exponents. So each Si is raised to the exponent of Ni, and we'll soon understand why that is. Another example is called Michaelis-Menten kinetics, and a fairly general way of formulating that, but that still only really is sort of applicable if Ni is equal to 1 or minus 1, for the substrates, is to form the product not of the concentrations or the amounts, but of this term. So it's the concentration divided by the concentration plus a constant. And we'll soon understand what this property is. And there is here again a leading constant here and a leading constant here. And the final sort of recipe that we'll go through is Hill kinetics. And then it's exactly the same. It's just that you have the exponent here of the concentration and also of the Hill of the Michaelis-Menten constant. Okay, so now we've seen the formulas. Now let's understand a little bit intuitively what they do. So for the mass action kinetics, we can take this this example again. 2A plus B are the substrates, and then we simply take a leading coefficient K1 times A, concentration of A, squared because we have the 2, and times B because that also appears as a substrate. And now we can also easily understand why it's squared 2. And that's because here 2A is the same as A plus A. So it could say A plus B. And if it would be like that, then since it appears as multiplications in the mass action kinetics, it would be A times B, because the plus turns into multiplication. And A times A is simply the same thing as A squared. So that's why the stoichiometric coefficient here, which describe plus here, becomes exponents here. It's because of this very simple idea. Okay, so let's understand a little bit what this expression is doing. So here we have A, concentration of A increasing, and here we have the reaction rate. So let's see two things. The first is that the reaction rate goes down to 0 no matter what B is doing. So even if B is super big, if you don't have any A in mass action kinetics, there will not be any reaction happening, which is typically sound. And the other thing is that there is no limit for how big the reaction rate can become. It just grows and grows and grows and grows forever. So if you want to have such an upper limit for the dependency of one of the substrates or one of the inputs, then you should instead not just multiply with the concentration itself, but with this expression here. So A divided by Km plus A. And why is that? Well, it's because when A gets bigger and bigger and bigger and bigger, eventually it will get much bigger than Km. And then this denominator here will basically be A. So it will be A divided by A plus something very small. So it's essentially A. So A divided by A, that's just 1. So then this will be 1 times V max. So this expression never gets bigger than V max. It approaches V max. And that's why it's called V max, because it's the maximum value of V. And what about when you are sort of halfway there? So when A is of the same size, so when A and Km are the same, then it will be A plus A here, or Km plus Km, and here also Km. So Km divided by 2 Km, which is just a half. So when A and Km are the same, then the rate is half Vmax. So when A here is at Km, whatever value that is, then you have half the maximum rate. So that's the interpretation of these two parameters. And it's the same when you have these Hill expressions. It's just that then it becomes a little bit more switch-like. So it's linear here in the beginning. It behaves the same. You can't really see that it's bending off here in the beginning. It's the same here. It's the same here. But it's slow. And then suddenly it's very fast. And then it's almost maximum directly. And if you want this type of more switch-like behavior, then you should use this Hill expression instead. And H should then be bigger than 1, typically bigger than 2 also, so like 3 or 4 or 5 or something like this. Then you start to get this behavior. Okay, so I think we are ready for an example. So let's consider an example. X turns into Y, and here we have an input. So we have some kind of enzyme that catalyzes this reaction. And then we have a second reaction, which is Y plus 2Z that leads to the elimination of both of them. So 2 reactions. And the formula is basically the following. So we need to first identify what are the things that appear in the reactions that we need the differential equations for. Those are called the states. And then we need to make some assumption or talk to our collaborators or read the instruction in the example and figure out what are the assumptions, not only about which reactions that we have, but of their kinetic expressions. And then we just sum them up. And that's basically it to create an ODE in itself. If you also want to have information about the output, so how to compare with data, then you also need a measurement equation, and that together with the initial conditions form all of the parameters. And these things we will talk much more about in some other videos. So here the states are simply x, y, and z. U is not a state, it's an input because it's only impacting the reaction, it's not used by the reaction. That's why it comes in with an arrow like this and not like this. If it's like this, then it's a substrate. If it's like this, then it's only impacting the arrow. Okay, so x1, x2, x3 are here we choose amount. We could just as well have chosen concentration. And let's make some assumptions since we don't have any assumptions in this figure. So let's assume that the first reaction is linearly dependent on x1, but that there is a saturation, there is a maximum sort of impact that we can have of U. So when U gets really big, it starts to have a new impact. It's already played out its impact, so to say. So here you see that you can actually combine these two. So this is sort of like the mass action kinetics, and this is like the mechanismental expression. So it's just to sort of have the flexibility that you believe that your system displays in the operating conditions that the model should be valid for. So it's an assumption, and then you compare with data to see if the assumption is good or not. And for V2, let's assume mass action kinetics, and here we have a stoichiometric coefficient, which is 2. So that means that x3 here will appear with an exponent of 2. Okay, so we have two rate expressions, and the resulting ODEs are simply by summing the ingoing. So here x has no ingoing, only one outgoing, so it's minus V1. X2 has, this should be with a subscript. So X2 has one, or Y has one ingoing and one outgoing. And it's just stoichiometric coefficient 1 all the time for Y. But for Z, there is again a 2 that appears. And here it appears as 2 times, because each time the reaction flows, there are 2 Z molecules that are consumed. So the rate of change of Z is twice the rate of the individual reaction. Okay, so that's basically it for this video. But I also want to mention a few final things, which is that you typically also assume that you can measure something. So you typically have some data, and then you need an equation for that as well. And we'll talk more about that in future videos. And that has to do with estimating the parameters. And what are the parameters that we've seen so far? They're basically those that appear in the rate expression. So the Vmax and the Km and the K2. Those are the ones that we primarily encountered. When we talk about simulation, then we'll talk about the initial conditions, where to start the simulation. Those are also parameters, x0 parameters. And when we talk about comparison with data, then we also need to consider this parameter here, which is the parameter appearing in the measurement equation. So those are the parameters in the model. And again, so talk about this more later. And again, if you transport things between different compartments with different volumes, then the volumes will appear in the equations. So you will have the volumes here will appear in different places. And this is dealt with in a separate video because this video is already as long as I want it to be. So we are done for this video. So hope you liked it and that you can exercise yourself. Otherwise, ask questions when we meet.